Section 1.7 is all about three-dimensional figures. So by the end of class, you should be able to identify, find surface area and volume of three-dimensional figures. All right, so first of all, we need to look at a lot of definitions about them. So the first one is polyhedron. It's a solid with all flat surfaces, right? So no spheres, so thinking of like a basketball, softball, soccer ball, any of that. So none of that, because polyhedron has to have flat surfaces. A lot of the polyhedron, or all of the polyhedron, have what's called faces, and it's the flat surface of the figure. There are also edges. It's the line segments where the faces intersect. So two faces intersect and form an edge. Right? I'm going to skip down a little bit because I feel like it goes along with this. But the edges all intersect at what's called the vertex. Just like the vertex of the angle. So I'm down to here. And if we look, let me highlight. So vertex will do this color. So if I'm looking at this cube down here, there's a vertex, there's one, there's one, there's one, there's one, there's one, there's one, and all the way back here is one. If we are looking at edges, I'll just highlight a few of them, not all of them. So there's some of the edges, and then the faces is like the whole front here. Okay, so the whole front part. And then, of course, there's more. There's the top, the back, the left side, right side, and bottom. All right, so a prism is a polyhedron with two parallel congruent faces. Okay, so any polyhedron with two parallel congruent faces. And we're going to look at all these here in a little bit. Bases, this one's super important, especially when we go to find the volume. Bases are the two parallel congruent faces of the polyhedron. Okay, because they don't always set the figures on its base. Okay, so we can't always say, well, the base is what it's sitting on. Sometimes the base is, it's not sitting on it. So it's the two parallel congruent faces. All right, so regular prism, it's a prism, with bases that are regular polygons. So that should say bases, B-A-S-E-S, the regular polygons. And maybe I have fixtures. All right, a pyramid. It's a polyhedron with all but one face intersecting at the vertice. Okay, it's sort of like this tetrahedron here. It's a type of pyramid where they're all intersecting right here at the top. A regular polyhedron, it says if all faces are regular congruent polygons. So a cube would be a regular polyhedron. And there are 5 regular platonic solids, and they are listed here in this picture that I've sort of been referring to. All right, ones that are not listed there, we have a cylinder. It's a solid with congruent circular bases. So I will draw one here quickly. It won't be the best, but you'll get an idea. Just think of like a can, which I'm sure a lot of you have already. All right, so there's our cylinder. A cone has a circular base and a vertex. So think of like a waffle cone, maybe at Mikey's is more of a cone shape. A sphere, it's a set of all points in space that are a given distance from a given point. So let's see how good I can draw a sphere. Okay, sort of to show the three-dimensional aspects of it. Surface area, because here's where we're going to do a little bit of math. So it's the sum of the areas of each face. So you pretty much find the area of each face and then add them all together. There are formulas on your formula sheet. You're going to see formulas in this packet. I believe the formulas are actually different from one another. But just know, in general, for surface area, you find the area of each face and then add them all together. Okay? But then use whatever formula works for you. And then volume, it's a measurement of the amount of space that a solid encloses. So if I were to look at this cone here, volume would be like, all right, how much ice cream can I fit in there? Now, we don't want it like bulging over the top. Just how much can we get to fill the cone? Maybe I should do this in a different color. And then flatten it off at the top. All right, so that's all of our definitions for today. Let's take a look at our first example. There's a little bit of writing in these first couple. So the first one says identify the solid. So maybe it's easier if we have that down there. All right, and then we have to name the bases, faces, edges, and vertices. So this is where it can get kind of time consuming. All right, so we have, usually you guys have a paper, so I will have to make sure I put that paper up for you guys to access, other than just the regular polyhedra, because we used to make the shapes, but we'll see. So I need to made myself a note. So identifying these solids. This solid is a rectangular prism because we're going to be looking at, there's triangular prisms, rectangular prisms, pyramids, cylinders, cones, spheres. We're going to be looking at all of that stuff. So this one is a rectangular prism. And I'm going to go back up here and show you, because a prism, it's a polyhedron with two parallel congruent faces. All right? It's not a regular prism. We can't say it's a cube because it's slanted, and we don't know that all the sides are the same length. So that's the name of it. Now we have to label all of the bases. All right, so there's two bases. In this case, a lot of them appear to be, so for this one, we are going to say, okay, what is it sitting on? That's the basis, because if I look the left side, the right side, they're also parallel and congruent, top and bottom, front and back, so we're just going to pick the top and bottom for this one. So we have to go not necessarily in alphabetical order, so for this one, I'm going to do E, F, H, G. You technically only need 3 letters, but I like to do 4 that way. If we're reviewing the answers together, you don't have to question which ones are there. All right, so I don't want to do, and let me show you the difference here. I don't want to do E, F, G, H. You can see how that's sort of crossed it. You want to go around the perimeter of the object. So E, F, H, G. So one of them is E, F, H, G. And the other one is the bottom, and we'll do A, B, D, C. A, B, D, C. All right, the next one are faces. All right, there are 6 faces. Now I will say that I've seen sometimes they don't count the bases as faces, but they are. So we're going to go ahead and count all of them. So we have to name all 6 of them. So I'm going to do the 2 I just did. So E, F, H, G, A, B, D, C. All right, and now let's do F, B, D, H. So if that was the right side, now let's take a look at the left side of E, A, C, G. All right, and now I think we just have the front and the back because I have all those lines there. So now the front is C, D, H, G. C, D, H, G. And the back is E, F, B, A. E, F, B, A. All right, so we have 6 of them. All right, so we did bases, faces. Now we need edges. So edges is where all the faces meet. All right, so edges. I'm just going to count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are 12 edges. Now we just have to name them. So I'm going to start up top. I'll put lines through them. So G to E, E to F, F to H, G to H, F to B, B to D, D to H, all right, C to D, A to B, A to C, C to G, and A to E. We have all 12. And last but not least, we have all the vertices. All right, so vertices, remember, that's where the edges meet. So it's all the little points. So we have 1, 2, 3, 4, 5, 6, 7, 8. All right, so we have 8 of them. And these are just points, so we can just label them. So we have A, B, C, D, E, F, G, H. So there's all of them. All right, for this next one, because you're going to get some practice with this, we're just going to name it because all the faces and edges, we'll go over it, but there's a whole lot. So this one, we're going to name it by the shape of the base. So let's take a look. This has 1, 2, 3, 4, 5, 6. Okay, 6 sides, so that's a hexagon. This has 2 parallel bases, so it's a hexagonal prism. Okay, we can go ahead and count the number of each of these things. We'll do that anyway. So bases. All right, there are 2, okay, and they're the hexagons. Faces, there's 1 in the front, 1 in the back, so that's 2, 3, 4, 5, 6, 7, 8. So we'll say 8 total. Edges, let me erase all this. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. There's 18 of them. That is a lot. All right, now we have vertices. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's 12 vertices. All right, and our last one here, for some reason that went H-I-J. That's fine. This shape, you all should know, it's a little bit better than my drawing, but not that much better. It's a cone. All right, so a cone's a little bit different. So let's take a look. Its base, there's only one, and it's circle T. Okay, so we haven't really gone over too much with circles, but we name them by the center point. So circle T. It doesn't have any faces, no edges, because it doesn't have any flat surfaces. So now vertices, because it does have a vertex, because it has one, and that is at W. And then we're going to make a little note that there's no faces or edges. All right. Next key concept. All right, so here's looking a little more at what our prisms, pyramids, cones, and cylinders look like. So you can see the prism there. We can also have triangular prisms. Our pyramid, we can have triangular pyramids or rectangular pyramids. A cylinder, it's like the shape of a can or the bottom part of the silo, and then we have our cone. So these are the formulas for surface area, volume, and just to give you a little bit of a refresher, P, they do have down here, it's the perimeter of the base. So remember to find perimeter, we add up all the sides. Capital B is the area of the base. All right, there's a few more things they have in here. Lowercase h is the height of the object. What else is in here? Oh, little l is the slant height or length. I think they use T for surface area. I usually just do an SA for surface area. But I think that's it. Oh, for a cone and a cylinder, R is always your radius. And then you guys know pi, hopefully, is pi. All right, so I'm just going to go ahead and use the formulas that are up here, but feel free to use the ones on your formula sheet. They all mean the same thing. You'll get the same answer, but I do believe, if I remember correctly, some of them are slightly different. So for example 2, it says use the figure to the right to answer the following questions. Part A, we have to find the surface area of this cone. So for surface area, I think about wrapping a present. You want the wrapping paper to get on every single surface of the outside. So that's what we're trying to do here. So if I'm looking at this formula above for surface area, we're using this formula. So it's T, or I use SA for surface area, is pi times the radius times the slant height plus pi times the radius squared. So pi is just a number, so I'm going to leave it there. The radius, hey, they did give me the radius. That is 3. My L, which is my slant height, that is this in this case, because the regular height, let me get a different color, goes from the very bottom to the top. So that's actually your height. So let me put the H there in that figure so you have it. All right, so in this case, L is 5 plus pi plus r squared, so 3 squared. Another thing I will say is they don't always give you the slant height. Sometimes they'll give you the height and they'll give you the base, and we're expected to use Pythagorean theorem to find that. So I'm just going to go through that now quickly and show you. So right here would be our 90-degree angle. So the slant height's what we're trying to find. So it would be 4 squared plus 3 squared equals c squared. So we get 16 plus 9 equals c squared. C is equal to the square root of 25, so c equals 5, which is exactly what they gave us there. So it works out. All right, so down here, all we have to do is just multiply everything. So we would have 15 pi plus 9 pi, okay, which if we wanted an exact answer, it would be 24 pi centimeters. It is area, so we do squared. Or if we multiplied those, we would get approximately 75.4 centimeters squared. Okay, so either one, exact or our estimate for surface area. And again, you don't have to memorize these formulas. You'll be able to use your formula sheet. All right, now part B for volume of that cone. So if we look at the formula, volume is 1/3 pi r squared h. So the 1/3 stays, the pi stays. Now my radius is 3 squared. My height is 4. So order of operations, 1/3 pi, exponents. Now I can multiply. I'm going to do 1/3 of 9. So I get pi times 3 times 4. Running out of room, so let's go up there. So 3 times 4, well, that's 12 pi. So if I'm leaving it an exact, it would be that. Now this is volume, so it's cubic meters. And an estimate of this would be 37.7 centimeters cubed. And that is for volume. All right, so moving on to our last example for today. There's no picture, so maybe we will have to draw a picture. It says Mike is creating a mailing tube which can be used to mail posters and architectural plans. The diameter of the base is 3 3/4 inches and the height is 32.5 inches. How much cardboard, does Mike need to make the tube? All right, so he's creating a mailing tube. Tubes are generally what shape? They're generally cylinders. So thinking if you were like putting a poster in something, you would put it in a tube. So there's our tube. All right, it says the diameter of the base. Let me get a color other than that. Okay. Is 3 3/4 inches. I prefer to either use decimals or improper fractions. I'm going to go ahead and use decimals. Whoa, that is really thick. Okay. Let's try this again. So the diameter. Diameter goes the whole way across, goes through the center. That is 3 3/4, so 3.75. That is inches. Can fit it in there. The height is 32.5, so 32.5 inches. Okay, so how much cardboard does he need? So we need to think about that. If it's asking how much cardboard he needs to make this, are we trying to find surface area or volume? So are we having the cardboard fill the inside? And if you ask yourself that question, it is no. We just want it to make the outside. So we're actually just looking at surface area. All right? So the formula, if we're using the ones above, is 2 pi RH plus 2 pi r squared. Okay. If the diameter is, I think I only have this in fraction form. If the diameter is 3.75, the radius is half of that. So if we take 3.75, because look, we need the radius. So radius is half of the diameter. 3.75. So it's 1.875. Okay, that's what the radius is. So now we can substitute everything in. So 2 pi times 1.875 times 32.5 plus 2 pi times 1.875 squared. All right, so multiplying all this through, except for pi, I get 121.875 pi plus 7.03 pi. So now this, if I multiply by pi, I get 382.88 plus 22.09. And that gives us, I should do approximately 404.97 square inches. Okay, it doesn't ask. So if we're doing this, you probably can't go to the store and say, I want 404.97 square inches of cardboard. So we would probably have to round it to about 405 square inches of it.